Inductive reasoning, it's easier, but it doesn't always work. Deductive reasoning always works, but it's harder. Okay. Any questions? So let's go ahead and use some of our newly refined reasoning skills and apply them to these number patterns. All right. So first we're going to start off with this one. Of course, this is section 1.2 now. So guess the next number. 2, 9, 16, 23, 30. Is that pretty straight? Okay. How'd you do that? Exactly. So this is probably the most basic of all number patterns. It has a general name. Aside from just saying +7 every time, it's got a general name. It's called the method of common difference. Now, why is it called that? Exactly. It's called that because if you're to look at 2 and 9, you would say the difference is 7. If you look at 9 and 16, the difference is 7, etc., etc., etc. So one way to think of this is that the rule is +7. Another way to think of it is that the difference between any two consecutive numbers is 7. Okay.
But could it be applied to any other pattern that you just added using the number all the time?
If
instead of +7, it was like +5 or like.
That would be the method of common difference also.
So it could be for any like number.
Oh, of course. Sure. Okay. So, for example, Daniela, what about this one? Oh, I'm sorry. This is a little trickier. I figure we already understand the first one. So now we're going to do something a little more clever. 6, 10, 16, 24, 34, 46. Exactly. So what's the next number going to be? Does everyone catch this? Jessica, yeah? Okay. Yeah, next number is going to be 60. Now, how do we get this? So, if we try to write down these differences, we get 4, 6, 8, 10, 12. So clearly, what will the next difference be? Clearly the next difference is going to be 14. It's going to make that number 60. Now this pattern is obvious at this point, but there's a way that we can write this down to see that it's a method of common difference. What do we notice about 4, 6, 8, 10, 12? Okay, yes. How do you get from one to the other? Add 2 every time. So what do we have to do? Got to do it again. And there you go. So we actually had to apply our technique or our process an extra time. You dig? Plus, this helpful little notation here is a way to write it down. Excuse me. An arithmetic sequence is exactly this first one. It's the method of common difference applied in the very simple way. Geometric is by multiplying, so it's different. Okay, so is this pretty straight? Alright. So now I'm going to throw a curveball at you. Make a sequence using this method. I've already filled in the first bits. Again, using the notation that I've established. Yeah. What do the 4s represent? Exactly. So for example, what's the next number that you can fill in? Where does the 12 go? Exactly. And then what? Okay. But are we done? No. Because this is not the sequence that we seek. What is the sequence that we seek? Exactly. So after 6, what comes next? Check it. Right. 6 plus 8 equals 14. Good. There you go. Oh, and we can tack on 1. Actually, that's all the dashes I put, so that's good. So that was very clever. You guys just created a new sequence. And check it out. Let's rewind a little bit. What if I gave you this sequence? 6. Let's say, in fact, that I gave you this sequence. 6, 14, 26, 42, 62. And I said, what's the next number? You would have looked at me like I was bonkers. Right? Yeah. Right. But you guys just did it. So, Jessica, does that make some sense? Okay. Let's see. So, Rian, any questions? No? Okay. See, do I have some... Oh, okay. Let me give you... Let's see... Okay. Let me give you one to work on. Okay, let's do this. Okay. Now I've given you a moderately challenging one, so be ready to put a little work in. Okay, so you had some time to work on this, so now let's, I'm sure some people have something, some people don't have something, but let's talk about it. So, what's the first thing that we do? Yeah, find our differences. So, okay. So what is this difference? This is 3/3. Next difference, 666. Next difference. Yeah. Sorry. Okay. And then the next one, 1690. Okay. So we did one layer. That didn't do it. Next. Do it again. Okay. Now did that do it? No. Right. You can, so the thing is this, you can now see what the pattern is, but seeing what the pattern is basically just means that you've done the next layer. Because what do we get in the next layer? 120 and next? Okay. So that's the clear pattern. So this is sort of the, now we have the pattern. That's part one. Part two is, what do we now do in order to find the next number in the sequence? Exactly. The pattern is, on this layer, the differences are always going to be 120. So you can fill in 120. In fact, you can fill in as many 120s as you like. We only want one though. So once you fill that in, what next number can we fill in? Right, that tells you immediately that this is 696. Now knowing that, now what number can you fill in? Next you can do this one, which is 2394. And then finally, you can go up and do this one. Okay. Now notice that with a little bit of work, we could now find every single number in the sequence. I only asked for one, so we'll stop there. Okay. But does this make sense? Okay. So step one, get it down to the layer where you actually find what the pattern is, and then once you do that, you can then fill it in as far as you like. One number is probably enough. Okay. So that's the method of common difference. We're not going to do much more with that in this class, but this actually, if we were to follow this actually gets into a big, if we were to follow this and do this a little more abstractly, this actually gets into a really important branch of mathematics. Difference equations, discrete dynamics, but that's if we follow it a bit further. We're going to hold here. Okay. So, next bit. Surprising sums. Alright. So let's just add up odd numbers. 1 plus 3, obviously that gives you 4. 1 plus 3 plus 5. 1 plus 3 plus 5 plus 7. 1 plus 3 plus 5 plus 7 plus 9. Guess. Next one. Yep. So what's the rule? Adding what? Okay. Adding up which odd numbers? Okay. Which positive? Consecutive odd numbers. Gives you what? Adding up consecutive odd numbers gives you what? What's special and unique about the result? 4, 9, 16, 25, 36.
Oh, they're all squares.
They're all squares. And in fact, so we can say this. So does everyone see that now? Yes, and Alicia, we with? Okay. So we can actually say this a little precisely. So let's do that. Adding the first n positive consecutive odd integers gives you n squared. Now I'm just going to take a moment here to show you how to write down in a sort of more mathy kind of way, because already saying the first n positive consecutive odd integers, that's already kind of mathy, I agree. But I want to show you how to write this down symbolically. 1 plus 3 plus 5 plus dot 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 plus 2n minus 1. So what the heck does this mean? Well, we know where the 1, 3, and 5 comes from. So what does the dot 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 mean? Right. Oh, exactly. Somebody learned this before. It means continue the pattern. So continue the pattern is something that is in fact in a large part what we're talking about today, is seeing the pattern. So the pattern is you just go to the next odd number. But then what this is saying is stop at 2n minus 1. Now what the heck is 2n minus 1? Right, it's a formula for what? Okay, well let me ask you. 2n. What does that mean? 2n has to be an even number. Exactly. Because it's 2 times something, so it has to be even. So if I do 2n minus 1, what does that have to be? That has to be an odd number. So 2n minus 1 is the way that mathematicians write down a general odd number. Also, depending upon your particular calculation, some people use 2n plus 1. Here we want to use 2n minus 1. Next bit. What is the sum of the first n positive integers? Or in other words, 1 plus 2 plus 3 plus blah blah blah. And I should put plus n. Okay. So in this case, this notation is a little more clear. We're going 1, 2, 3, da da da, all the way up to n, and adding all those integers together. Well, let's see. Let's do this. There's a funny story that goes along with this problem. Long time ago, a teacher in a classroom, I don't mean me, I mean like hundreds of years ago, a teacher in a classroom said, I want to keep the students busy for a long time. So I'm going to tell them to add up the numbers 1 through 100. So 1, class, do 1 plus 2 plus 3 plus 4 plus 5 plus da-da-da plus 99 plus 100. Teacher said, that should give me time to read my book. Well, about 20 seconds later, one of the students walked up to the desk and said, "Teacher, I'm done." Teacher said, "That's not possible. Go back to your desk and finish your work." The little student said, "Yeah, here it is." Now, how is it possible to add this up? And mind you, without a calculator. How is it possible to do this so quickly?
Well, you need the 100 on the side and then 99 plus 100 is 100, so then you just do the 900 so you just do that, and then you do that all the 100, and then you don't get off with it.
That is a really clever way to do that. Does everyone see what he's talking about? Okay. So what Jonathan said is pair up the numbers 99 plus 1, 98 plus 2, 97 plus 3, da 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 da. Okay. That is almost the same as what this bright young student did. This student said, let me include the 100. Let me pair up the numbers the way that they are. Now, if you pair up the numbers the way that they are, what does each pair make for a sum? 101. And how many of those do we have? Right. Well, it depends how you think of it. You can either think of it as 50 pairs, or a standard way to do this is to say, I'm just going to add all these things, and I get 101, 101, 101, plus, plus, plus. So, and how many, the way I've written it here, how many 101s do I have? Well, not the way that I've written it. The way that I've written it, you get 101 times 100. But that's not the sum of my original sum. What do I have to do? Right. I've got 2 of my original sums. So I have to divide by 2. So Jonathan, this is the same basic idea of what you said. It gets rid of the dangling 100 and 1 or 2 other problems.
So wasn't he intending to add all the numbers up to 100?
Yeah. And that sum is 5,050. Right. Much quicker than lining all the numbers up in a column, 100 numbers in a column, and trying to add them one by one. Alright. So the name of this young student was Gauss, and he went on to become probably one of the couple of greatest mathematicians of all time in the history of the world. Okay. So now we're going to use, I've given you one example, but we're going to use the idea of this example to actually come up with a general formula, not for the first 100 numbers, 100 positive integers added together, but just n integers added together. So if you were to have n integers added together, what would happen? Well, when you write 1 plus 2 plus 3 plus blah 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 all the way up to plus n, again, reverse it so you have n plus, well, the next one is n minus 1 plus do all the way down to 1. Now pairwise, when you add these together, what are you going to get? Right. each pair, when you add it together, what are you going to get? Yeah. What does that pair give you? N plus 1. What does the next pair give you? N plus 1. So each of these things is going to be N plus 1. Now, how many of them do we have? We have N, because it's counted quite literally by our original sum. 1, 2, 3, 4, 5, da, 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 all the way up to N. So, we've got N plus 1, N many times. So this is going to be N times N plus 1. But now what do we have to do to get the result that we want? Divide by 2, because we've counted everything twice. That was the pairing. And there you go. That is the formula for the sum of the first n positive integers. 1 plus 2 plus 3 up through plus n. And we just, with a little prodding from me, derived it together. Now, by the way, is this inductive reasoning or deductive reasoning? This was deductive reasoning. We did it algebraically, and we now have a rule that always works that we can apply to any case. If I ask you what's the sum of the first 20 positive integers, you don't have to sit there doing 1 plus 2 plus 3. You just plug it into the formula. Yes?
So on top, the 101 would be N plus 1 and 100 N plus.
Exactly. Okay. So now let me say this. I do not. Here we go. I do not expect you all these formulas that we're working out. The first n odds is n squared, and the first n integers, the sum of first n integers, positive integers is n times n plus 1 over 2. I don't expect you to memorize these formulas. This topic is problem solving, and problem solving is not about solving a problem once and memorizing the formula or the answer. What I do expect you to know is the method. So, for example, in this last problem, what was the trick or the method that we used in order to get the answer? Sorry? Did you say pair them? Pair them up, exactly. So by pairing them up, we could, in a very quick way, figure out what the sum was. So using that one technique, we can now solve this, not only solve this problem again, but we can solve slightly different problems, which will result in a completely different formula. And those are the sorts of things that you'll be doing on the homework, applying this technique to similar problems. Okay. Any questions? So, last bit for today. This is another pattern, and this one has, I'm going to show you a nice visual interpretation. So this topic is called figurate numbers. So what does that mean? Numbers that come from a figure. How? I'm going to draw you the picture. Triangular numbers. What's a triangular number? Yes. How? Okay. So that's what I'm going to show you. Okay. So first, this one. Okay. Next, I'm going to draw a triangle, but I'm going to add on. So I'm going to add another side and grow the triangle. So I'm going to do that again. So now, given this, so how many points do we have in the first case? Just 1 point. With the next triangle, we had 3 points. How many points in the next triangle? 6 points. Okay. Next triangle, let's see what that looks like and how many points there are. Grow the triangle. Grow the triangle. And grow the triangle. How many points do we now have? Okay. Is there a quick way to figure out how many points there are? Absolutely. Because how many points are we at? Because what do we do to get from one figure to the next? All we're doing is adding a layer. So all we've done is taken the previous triangle and added 4 points. So in the next triangle, how many points will we have? How many points are we going to add in the next triangle? 5. So how many total points will there be? And how about in the next triangle? What are we going to add? We're going to add 6, yes, and get 21. By the way, this procedure should sort of remind you of something. What does this remind you of? Method of common differences, absolutely. Okay. Now it turns out that on one hand we can use the method of common differences, but that only tells us the next number. We also have a general formula for any individual number. For example, if I said, tell me how many points are going to be in the 20th triangle, you wouldn't want to use the method of common differences, because you have to figure out every triangle in between. Turns out there's a nice general formula. So far here I've got the first triangle, second triangle, third triangle, fourth triangle, fifth triangle, and although I didn't draw it, we figured out how many points are in the sixth triangle. So we call these T1, T2, T3, etc. Not a series of Arnold Schwarzenegger films, but rather a series of triangles. Okay. So now here's the general formula. To find the number of points in the triangle with n layers, or in other words, the nth triangle, there's your formula. Wait, that looks, what? It's the same as the one before. Why is it the same as the one before? What's the method? Right. Why is this problem actually the same as the problem we just did? Look at, for example, the third triangle. What makes up the third triangle? Right, and how are those 6 dots arranged? 1, 2, 3. How about the next triangle? How are those dots arranged? 1, 2, 3, 4. Next one, 1, 2, 3, 4, 5. So this is actually just a visual representation of the sum of the first n integers, n positive integers. Pretty patterns are everywhere. That's one of the morals that I hope you take away from this this section of the course. Okay. That's triangles. Next, square numbers. Alright. So the first one is always, we're just going to make 1 dot. Okay. So this is the first square number, and its number of points is 1. What does the next square look like? Well, it's just going to be 1 little box. And how many points? So that's the second one. And how many dots does that have? 4. What does the next one look like? We're going to add another layer. So this is the third square. How many points are there? Then for the fourth one, yeah. Okay. So in fact, the way that this goes should be fairly obvious, because when we draw these squares, what do we actually just have? Yeah, it's just a square. So for example, in the 6th square, yeah, we're going to have 36, because how are the dots arranged? They're in a square, so we have 6 rows of 6. Wait. Yeah. If you just look at the way the dots are arranged, here we have 4 rows of 4. In the next one, we're going to have 5 rows of 5. And you can see that in the next one we're going to have 6 rows of 6. So this is just 16, 25, 36. Okay. So there you go. So very clearly, if you want to know the number of dots in the nth square, it's just n squared. I bet that one you'll be able to remember. Okay. Next one's a little bit of fun. Pentagon numbers. So this one's going to be a little different. So the first one is just a dot, 1 point. Next one we actually have a pentagon, and boy, I'm going to try to draw a pentagon. There you go. Okay. And how many dots do we have now? 5. Yeah, thanks.
In the fourth section,
Uh-huh.
more than 25 dots.
Oops, you're right. There we go. Okay. That was the picture for that one, quite right. I got carried away. Okay. So now we're going to try to be very clever about drawing these pentagons. So let's do it. So we're going to start with the basic pentagon. Now we're going to add another one. Get this right. Here, 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 here. No, wait. Nope, that's not it. I know what I did. That one's too short. Okay. This one's too short. Drawing pentagons is hard. Okay. Kinda lopsided. But that's it. So my third pentagon has how many dots in it? 12. Okay. My fourth pentagon, I'll try to draw it. Okay. Like this, and then this will be longer. Like this. No. That's the problem. Okay. That should be joining up. There we go. Okay. Now how did you get 21? Okay, so you think it should be 22. So let's check it. Is it 22? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Absolutely. So Terrell very cleverly used this method of common difference. Because each time you add a side, how much more are you adding? Well, here we've added 4, here we've added 7. So what does that tell you? You've got to do another layer that's going to give you 3s. And from the overall pattern of all these figurate numbers, we've noticed that that's as far as we need to go. From now on out, all the common differences in this layer will all be the same. So he figured out that the next common difference is going to be 10, which should give you 22 dots, and indeed it did. So this is the way you actually tying this together with the common differences is actually extra credit level stuff and very clever. So that's good work. And finally, let me show you the formula, because there's actually a formula for pentagonal numbers. Instead of finding them one by one using common differences, there's also a formula, and it's this fun thing. Okay. Now again, I don't expect you to be able to figure out these formulas on your own. I don't expect you to be able to memorize the formulas. I expect you to be able to do this sort of work in figuring out similar problems. Okay? Any questions? Okay, good.